I've fallen, and I can't get up.
I have fallen and I can't get up.
I've fallen and I can't get up. The cry of the elderly. Many elders experience this unfortunate event due to the underlying causes of osteoporosis. Osteoporosis affects 13% of men and 50% of women over the age of 50. This disease attacks the bones in the spine, wrist, and hips. Bone is constantly being replaced, and osteoporosis attacks the process of bone replacement by slowing the creation of new bone. This results in an increase in bone porosity and thinning of bone walls, which causes the bones to become brittle. Over time, repeated axial forces can lead to fracture and breakage of deteriorated bone. How do these axial forces affect the vertebrae specifically? The best way to understand the effect that axial forces have on a material is through Poisson's ratio. Poisson's ratio is the relationship between lateral and axial strain in a material when axial forces in the form of compression or tension are applied. Poisson's ratio can be positive, 0, or negative. A positive Poisson's ratio material features a negative strain value for either the axial or lateral strain depending on the direction of the axial force. Taking a positive Poisson's ratio material and applying an axial load will result in lateral deformation in the form of expansion or contraction. Most materials have a positive Poisson's ratio and experience this behavior. Examples include rubber, metals, and polymers. A 0 Poisson's ratio material features a lateral strain value of 0 regardless of the direction of the axial force. Taking a 0 Poisson's ratio material and applying an axial load will result in no lateral deformation of any kind. Some materials naturally have a 0 Poisson's ratio and experience this behavior. An example includes cork. A negative Poisson's ratio or auxetic material features a positive strain value for either the axial or lateral strain depending on the direction of the axial force. Taking a negative Poisson's ratio material and applying an axial load will result in lateral deformation in the form of expansion or contraction, which is the opposite of that found in positive Poisson ratio material. Auxetic materials are rarely found in nature, though living bone tissue is suspected to be an auxetic material. All of the following models have equivalent forces applied of approximately 200 kilonewtons, which is exaggerated for visual purposes. The average human spine would fracture at an applied load of around 3 kilonewtons, or the amount of force created by a 500-pound car crashing into a wall at 30 miles per hour. A fixed support was applied to the bottom of each model, leaving it fixed in place. Then, a force was applied to the top of each model to provide the simulation shown. The simulation's purpose is to demonstrate the overall concept of each Poisson ratio type. The forces are not necessarily evenly distributed, accounting for any non-uniform stretches in the animations. Here is a 3D printed model of a lumbar vertebrae. As osteoporosis strikes, the interior body of the lumbar vertebrae deteriorates and compressive forces build up, causing the vertebrae to collapse. Applying auxetic material will allow compressive forces to strengthen the applied material and prevent the compression of the spinal cord under load. This will result in the vertebrae maintaining its integrity and no longer experiencing the same strain. This test shows a 3D printed auxetic structure in tension. Due to the design of the sample, tension was the only way to visually demonstrate that it is auxetic. When axially compressed, the sample would have behaved as expected and the lateral length would decrease. We can conclude that auxetic material is the best choice to assist an osteoporotic vertebrae because auxetic materials are both rigid and elastic, the properties of which can be tuned to the application. Auxetic materials become stronger in compression as their density increases due to the collapsing of the structure into itself. Auxetic materials compress laterally as a compressive axial force is applied, which can prevent undue stresses from occurring on existing bone, and The ability to tune the material through the manipulation of its structure gives us the desired material characteristics to make biocompatibility a simpler process.